Hi everyone and welcome back to PrepFusion. I am Anish and today we will start with the lecture 26 of our machines subject. So today we will discuss about whatever homework questions I gave you, and also we will discuss about shunt series and compound DC machine. All these three types of different machines we will discuss about this. Okay. So let's start with this two questions which I gave you as homework. This one was the first question that I gave you as homework. So let's solve this question. So here we have a 200 volt 2000 rpm 10 amperes separately excited DC motor. Okay, has an armature resistance of 2 ohms. So whenever these kind of question comes, either you draw the circuit diagram or you write down the data. So whenever this is given, right, 200 volt 2000 rpm 10 ampere. So this 200 volt is actually not the generated value, it is the terminal voltage. Whenever a voltage will be given, unless and until specified, it will be generally the terminal voltage, right? Terminal voltage. Okay, so my V T will be equals to 200 volts. My speed, like it is whatever is given here, it is a rated speed. This is the rated speed. So n rated is basically 2000 rpm, and the current 10 ampere is the rated current of the armature. So these are the rated specs, right? So Ia is 10 amperes. Okay, full load, separately excited. So field current will assume it to be constant. Has an armature resistance of 2 ohms. So Ra is of 2 ohms. The rated DC voltage is applied to both the armature and the field winding. So whatever is the rating of the both the armature and field winding, this is this voltage only we are applying it. And field winding has its rated voltage, we are applying the rated voltage. If the armature draws a current of 5 ampere from the supply, determine the torque developed by the motor. So they are asking what is the torque developed by the motor if I know the armature current Ia2 is 5 ampere. How do I find out the torque developed? Have we discussed anything about torque? Yes, right. One thing I know, that the output power at the shaft is basically EB into Ia, back EMF into armature current, that will be equals to omega speed of the rotor shaft into the torque developed torque, right? Correct. This is what we have discussed. So what things do I know here? I know the armature current. Do I know EB? I can find out EB, right? It's very easy. It's like a just a DC circuit, right? So separately excited. So here I will have a resistance Ra, and here I will have EB. But do I know EB2 really? Do I know EB2? I don't know EB2, right? I just know my VT. They are telling that they are applying a rated voltage. VT is equals to 200 volts, right? 200 volts. And current here is Ia2. Will I be able to find out the EB now? Yes, very easy, right? Very easy to find out the EB. What is the EB? EB2 will be equals to VT minus Ia2 Ra. Okay, so VT will be equals to 200 minus Ia into Ra. What is Ia2? Ia2, they are telling that in the second case it is taking 5 amperes of current. So it is 5 into Ra. Ra is 2 ohms, right? Which we had already written it down. Okay, why is not? Something is wrong. 2 ohms. So it is 5 into 2. So this will be 190 volts. Now I know my EB2. I have got my EB2 here. I have got my I know Ia. I have to find out the torque developed. Do I know omega m? Nowhere they have mentioned the speed in the second case. How do I find out the speed in the second case? So again we have to come back to this basic formula. What is my induced? This is the induced EMF, right? Induced EMF. So I know my induced EMF, which we have already discussed, that my induced EMF E is proportional to the flux per pole, which will not change for a separately excited unless and until mentioned, number of conductors, speed of the rotor into the number of poles. So all these are actually constant, right? This phi, z, p all are constant. What is changing? Only the speed is changing. So I can directly find out the speed because I know EB1. Do I know EB1? I don't know EB1, but I can find out EB1, right? What will be EB1? EB1, the developed voltage in the first case, back EMF in the case 1. It will be Vt is same only 200 minus the rated current. When it is firing rated current, it is 10 into the armature resistance, that is 20. So this will be 180 volt. So this will be very simple, that my EB1 divided by EB2 will be equals to N1 divided by N2. So EB1 is 180 divided by EB2, that is 190, equals to N1. N1 is they have given me the initial speed, right? When current was 10 amperes, it is 2000 rpm. So this will be 2000 rpm. And in the second case, I don't know what is N2. This is what I have to find out, right? So from here I can directly find out the values. Basically this will be 190 into 2000 divided by 180. This will be N in the second case, right? In the second case, the speed will be 201.11. 2011.11. This is in rpm, remember. But here, right, what is the unit here? It is radian per second, right? Radian per second. How do you convert into radian per second? So one formula you can remember, that omega equals to 2 pi n by 60. If you want to remember, you can remember this formula. I can derive it as well. So what does n mean? N means rotation per minute. Let us convert this into per second. So if I want to convert this into per second, it will be n by 60. Very easy, right? Now it means in every second I am doing this many amount of rotations. So how much radians am I moving? Because one rotation is 2 pi, right? In radians. One rotation, one whole circle is 2 pi radians. So n rotations will be what? N rotation will be 2 pi n. So that's why it gets replaced with 2 pi n. My unit is radian per second. So that's why omega is 2 pi n by 60. Very simple. That's how you can do the conversion. Very simple and easy to understand. Now we can finally find out the torque in the second case. Torque in the second case will be omega is 2 pi by 60 into 2111.1 into omega into torque, right? Omega will be here only, right? So omega into torque will be equals to the EB2 into IA2. So what is EB2? EB2 is 190. So it will be 190 here into IA2. What is IA2? IA2 is simply 5 ampere. IA2 is simply 5 ampere. So from here I can easily find out what is the torque. So what is the torque? Torque will be 190 into 5 into 60 divided by 2 into pi into 2111.1. So this will be 4.3 Newton meter. This will be the torque basically. So this will be the answer for this question. 4.3 Newton meter will be the answer for this question. So unit of torque is in Newton meters. Okay. Let's now move on to this next question. So next question is, a separately excited DC motor drives a fan load where the load varies proportional to the square of the speed. So a motor is driving a fan load where they are telling the load varies proportional to the fan. So what is load? I told you, right? There are two types of current: load current and field current. So load means basically the current across the armature. So they are telling me that the load current varies directly proportional to the speed of the motor. Okay, this is one relationship that I know. When a voltage of 100 volt is applied, when a voltage of 100 volt is applied to the motor, uh, it draws 8 amperes of current and runs at 500 rpm. So you always write down the data. DC machine question will be very big. You just have to write down the data. So when my terminal voltage V is 100 volts, my motor IA1 in the case 1 draws a current of 8 ampere, and my speed in the case 1 is 500 rotations or revolutions per minute. Okay. Determine the applied voltage required to increase the speed to 750. So what will be this is V1, what will be the applied voltage, I don't know, to increase the speed N2 to 750. They want to increase the speed N2 to 750. So if my speed is increased to 750, can I find out the current, how much there will be increase in current? Because I have this relation, right? I will use this. Also find the corresponding armature current. Very easy, I can find it out. Assume the armature resistance Ra to be 1 ohm and neglect this brushes and losses, right? So how much current I will require? Again, this relation I know, right? The current is proportional to the speed square. So if I just divide these things, Ia1 divided by Ia2 will be N1 whole square divided by N2 whole square. So Ia1, I already know what is Ia1. Ia1 is 8 amperes, right? So it is 8 amperes. 8 Ia2 I don't know, I have to find out the current in the second case, is equals to N1 whole square. N1 whole square. So N1 whole square is this 500 whole square, right? Divided by N2 whole square, that is 750 whole square, right? So from here I can easily find out my Ia2. So it will be 750 divided by 500 whole square into 8. So this will be 18. So my Ia2 will be 18 amperes. This will be my armature current in the second case. So this is the first part of the answer. This is one of the answer. What else they are asking? They are asking me the applied voltage. How much voltage I need to apply? I can simply, again, it's the same circuit, right? Separately excited. Flux is constant. So there is a back EMF here, and this is the voltage, right? V. This is I. This is Ia. So again, I have to apply that same thing. That what was the back EMF in the first case? Will I be able to find out the back EMF in the first case? Because ultimately, right, I have to find out the back EMF in the second case so that I can able to find out how much V I need. Because what is V equals to? V is equals to EB plus IA RA, right? So I have to find out the back EMF, but I don't know the back EMF, right? So I have to use the first case. In the first case, do I know the back EMF? No. But can I find it out? Yes, because I know the terminal voltage and the current and the resistance. So in this case, the back EMF in the case 1 it will be V1 minus Ia1 RA. Okay. So V1 will be 100 minus Ia1. Ia1 is 8 into RA. RA is 1. So this will be 92 volts, right? So in the first case, my EB1 is 92 volts. What about the second case? Second case, I can use the same proportional rule, right? So flux is not changing. Flux is constant. It is separately excited. Nothing is mentioned. So ultimately, my EB1 by EB2 will be basically N1 divided by N2 because flux is constant. So what I can do here, that EB2 is 92. Sorry, EB1 is 92. EB2 is EB2 only. N1 Initially, what was the speed? Initially it was 500, then it becomes 750. So this will be 500 divided by 750. So my EV2 will be equals to 750 divided by 500 into 92, 138 volt. So this is the EB2. Now from here I can find out the terminal voltage. It will be EB2 plus IA2 into RA, right? EB2 is 138 plus IA2. IA2 is how much? IA2 is 18 amperes. What is RA? RA is, in this case, RA is, where did RA go? Yeah, RA is 1 ohms, right? So RA is 1 ohms. So this will be 1 ohms. So from here I can directly write what will be my V, terminal voltage. So my terminal voltage will be 156 volts. Very simple, right? So this will be the answer. These two will be the answer. Terminal voltage is 156 and my current is 18 amperes. So these are the kind of questions. Mainly you have to use this just proportionality, right? And KVL, KCL. That's it. DC circuits are very easy to solve. Okay, characteristics are there that will come into the end portion, but with this, right, mainly 50% you will be able to solve. 50% DC machine question you will be able to solve. So now let's come to another type of machines, that is shunt wanted. In case of shunt, it is a self-excited, right? What do we mean by self-excited? So if we see this time, right, I don't have any separate supply for the field winding. So whatever voltage is getting developed, that same voltage is used for developing the field. Okay, that's why it is called as self-excited. So if the generated voltage changes, the flux also will change. Okay, but as the terminal voltage generally is fixed, right? If it is generating something, the terminal voltage generally is fixed, so flux will not change. But just keep this in mind, it can change. So this time the field current is summation of two currents. So if it is acting as a generator, then it will leave from the machine. The IA current, armature current, will leave from the machine, and bit of it will be used to energize the field winding, and the rest of it will be used to provide the load, right? So in the generator case, my IA will be, if I apply KCL in this node, my IA will be sum of the load current IL or supply current IS plus IF. Sometimes this is called as the load current as well. Sometimes this is called as the load current as well. Now this was the summation of current. What is the field current IF? Field current IF, if I assume this winding has a resistance RF, will be equals to my supply voltage Vs divided by RF. That will be my field current IF. Okay, I hope you have understood this very basic point. Now let's discuss about the next thing, right? Let's discuss about the this was for the generator. This was for the motor, right? So for the motor, now the supply will supply the current for both the armature and the field winding, because it is a motor, right? It is acting as a load. Previously it was generating, so this will give the current to the field and the load. Now motor is the load, supply is the supplier, so I will supply both the field current and the armature current. So for a motor, my IS will be equals to IA plus IF if I apply a KCL in this node, right? And what about the this, right? What about the, again, the IF current is same only. IF current, the field winding current, is Vs by Rf. It will not change. One more thing, what is the generated EMF here? EG. It will be basically what? It will be Vs plus I into Ra. Simple KVL, right? Vs plus Ia into Ra and for motor your EB will be Vs minus IA into RA. Okay. So now, now this is the voltages basically. I hope you have understood. Again, you can easily write this down in terms of, now the losses have increased. Previously there was no losses, right? Previously the equation, if you remember, I was discussing about few copper losses. So there was losses here, right? Where is it? Where is it? Where is it? Where is it? Yeah, this was copper losses. This was getting lost in the armature. Now few more extra things will be added now. So if I see, if I multiply IA on both sides, right? If I multiply by IA, so if I multiply by IA here, what do I see? That my EG into IA will be the what? Will be the input power, correct? EG into IA will be the input power, because I am rotating the armature, due to which this voltage is getting induced, developed, right? So this is the W into torque developed, omega into torque developed, right? This is the input power basically. Okay, this will be equals to Vs into Ia. This is what? It is a combination of two things, okay? Plus Ia square into Ra. So what is Vs into Ia? Ia is equals to Is plus If, right? So this can be broken down into two things. This will be Vs into Is and another one will be Vs into If. So this portion is actually the output power, the power that the load will get, right? I will receive the power, output power here. This is what? Vs into If. What is If? If is Vs by Rf, right? So this can be further rewritten as Vs whole square R by Rf, right? What is this Vs whole square by Rf? It is the loss in the field winding. So field, this is known as the field loss, right? Field winding loss. Okay. And this is what this we already had discussed, is the copper loss. So I think you are getting a picture here that whatever input power I'm supplying, bit of it is lost in the copper of the armature, copper loss due to the armature. Bit of it is lost in the field winding due to its field resistance, right? It is also a kind of copper loss only. And the rest is whatever is left after doing all these losses is the output power that the output will get, right? It is simply output equals to input minus losses, just like that, right? So I hope this basic thing you have understood. Sorry, not output equals to, sorry, input equals to, output equals to input minus losses, or input equals to output plus losses. Anything will work. Same thing, same equation if you write here, same thing you will see that whatever input I am giving here, it is equals to output plus the losses in the copper winding of the armature and in the field winding. That is the exercise for you. Okay. So these are the self-excited machines. In this, the field winding is energized by machine's own armature voltage. The magnetic field builds up through residual magnetism. We will discuss about residual magnetism later on. Don't worry about these things. Okay. So this is the shunt wound meter, where the shunt wound machine, where the field winding is connected in parallel shunt with the armature winding. Since the field winding has high resistance, we discussed why it has high resistance in the previous lecture. It draws very small current, typically 2 to 5%. So the losses, so that we can minimize the losses, right? So it is generally used in constant speed applications. Why constant speed? Because the terminal voltage generally is fixed. If the terminal voltage is fixed, if I am using a motor, right, then I am providing the supply, and the supply voltage is generally fixed. So 220 volts will always be fixed. So if the terminal voltage is fixed, if I am fixing the terminal voltage, that means what? Here the flux is also getting fixed. So if flux is fixed, then the speed also will not change. Okay, if we are not changing the back EMF or the armature resistance, speed also will remain constant. That's why it is generally used in constant speed application. Okay, I hope you get the point. Why is it like, why is it thin? All those things we have already discussed in the previous lecture, right? Why? Because what is the losses? Losses is Vf's whole square by Rf, right? So we have to make the Rf very high to reduce the losses. We have to reduce the losses. To reduce losses, we have to make the RF very high. Okay. Now uh, next, so if I want to increase my RF, right, if RF is increased, then of course what is the current? Current is VF by RF, right? So if current is also increased, the current is also decreased, the field current is decreased, but I need good MMF, right? Good MMF, NF into IF. So if the current is decreased, then I have only one option left to increase the number of turns. That's why it has many turns, and why it has high resistance I have already discussed. And as it has high resistance, why it will be thin? Because what is my resistance? Resistance is rho L by A, right? If I want to make it high resistance, there are two ways to make it high resistance. Either you increase the length or you reduce the area. If I reduce the area, then also resistance will increase, right? So I will reduce the area, so it will be very thin. Cross section will be very thin. That's why the resistance will be increased. So these are the reasons why the field winding is like this. Okay, I hope you have understood this basic point. So same thing is written over here. Whatever we have discussed, same thing is written over here. So yeah, whatever I have told you, the same thing is written over here. Okay. The winding is designed to create a stable and constant flux relatively independent of load variations. So whatever is the load, as the terminal voltage is fixed, right? So the current across the field winding also will be fixed. So it will not change much. So the speed also will be fixed. Okay. So yeah, I hope you have understood this point. Now let's solve few questions. So first one I will do. Next one I will just show you the questions. I want you to try it out by yourself. Then I will obviously do the solutions, right? So let's solve this first question. A DC shunt motor draws an armature current of 50 amperes. So you keep on writing the things down, right? So if you are not comfortable in drawing the circuit, keep on writing the things down. So it draws an armature current of 50 amperes and its rated voltage. It draws it at its rated voltage. It is a motor. So this voltage is the terminal voltage basically. So V will be equals to 240 volts. The resistance of the armature circuit is 0.2 ohms. So the armature resistance is 0.2 ohms. Armature resistance is 0.2 ohms, while the field flux remains constant. So they have already told me it is a shunt field, but the flux is constant, right? It is not changing. Field flux is constant. It's not changing. Okay. Calculate the percentage change in speed for the same load torque. Calculate the percentage change in speed for the same load torque. Okay, we have to calculate the percentage change in speed for the same load torque. Okay, if after connecting this external resistance, so an external resistance is connected in series with the armature, right? While the field flux is constant, flux does not change because the terminal voltage has not changed, but I've connected a external resistance in series with armature. What will happen? Then there will be more drop across the armature, so the developed voltage will reduce. If the developed voltage reduces, then what? Speed will reduce because flux is constant, so speed will reduce. So intuitively this is how you can understand. So we have to calculate. That's why they are asking what is the percentage change in speed for same load torque and half of the load torque. So if the load torque is same, then what will happen? So we will discuss each and every case here, right? So let's solve this for the first case where the torque T1 equals to T2, right? So if T1 equals to T2 and in the case 1 my armature current is IA1 is 50 amperes. Okay, how will I solve this? So initially what is the EB1 when this external resistance was not added? So the EB1 is equals to V minus IA1 into RA. So this will be equals to 240 minus IA1, that is 50, into 0.2, right? So this value will be 240 minus 10, so 230 volts. Okay, 230 volts. So my EB1 will be 230 volts. Now in the case 2, what will happen? Case 2, they have told me that torque will remain same. Few things I know. I know omega 1 into T1 is the EB1 into IA1, right? This relation I know, right? This is what I know, correct? So one more thing I forgot to previously mention, that if my omega 1 is into T1 is this, right? Actually I can directly write my torque is proportional to the flux and the armature current. So armature current is already here, right? So my torque I can write, what is my torque equals to? So T1 is equals to EB1 EB by omega into Ia, right? T torque is equals to EB by omega into Ia, right? This is, you agree with this? So I can conclude two things over here. So my torque will be proportional to the armature current. This is what I can conclude. Also I can conclude my torque is proportional to the developed voltage or the back EMF divided by the omega. Okay. Now in turn, what is my EMF, induced EMF, proportional to? So my induced EMF in turn is proportional to the speed, right? And my omega is anyways directly proportional to speed. So omega is equal to 2 pi n by 60. So I can also, it is proportional to the phi flux. If I assume that the number of poles and number of conductors remains same, it is proportional to n into phi, right? So the speed gets cancelled out. So ultimately I can say that my developed torque will be proportional to the flux only. Okay, because speed is common and I am assuming that the number of poles and conductors are not changing. So this is the property that I can use over here. So I can directly write that the torque is proportional to flux into Ia. This will be used everywhere else. Okay, everywhere else this will be used. So this is also another very important relationship that we must know, and I have derived it, right? It's not like I'm mugging up things. Okay, so torque will always be proportional to the flux and the armature current. So they have already told me that the flux will not change. So phi 1 will be equals to phi 2. So the also in this case 1, torque is not changing, flux is not changing. So torque is not changing, flux is not changing. So armature current also will be same. So I can directly write Ia2 will be equals to Ia1. Why? Because my flux phi 1 is equals to phi 2 and my T1 equals to T2. That is the simple reason. So I can say that so current is not changing. So what will be the case EB2? EB2 same relation, right? It is my V terminal voltage. Terminal voltage does not change. Ia2 into R A plus the R series external resistance that I had to connect, right? RAC. So V terminal voltage is not changing. Terminal voltage will be same only, that is 240 volts, and I am adding a 1 ohm extra series resistance. So this will be 240 minus, what is the current? So what is Ia1? Ia1 is 50 amperes, right? Ia1 is 50 amperes. So this will be 50 into RA. RA is 0.2 plus RAC. RAC is 1. So this will be the EB2. So EB2 will be 1.2 into 50. So this will be 560. So this will be 180 volts. Okay. So that is what my EB2 will be equals to. That is what my EB2 is equals to, right? So from here I can directly comment about the speed. So I know again the developed voltage is proportional to the flux and speed because poles and number of conductors will be fixed here. So again I can use this same relation, EB1 by EB2 is equals to N1 divided by N2 because I have to find out the change in speed. So from here I can directly say what will be N2 equals to. So N2 will be equals to EB2 is 180 divided by EB1. EB1 is 230, I guess that point of time. It is 230. It is 230 into N1. What is N1? N1 is N1 is 6. Oh sorry, N1. Do I know N1? Okay. Okay, I don't need to know n1 anyways. I don't need to know n1 because I have to just find out the change in speed, right? So to find out the change in speed, so percentage change in speed, it is equals to the final speed minus the initial speed divided by the initial speed into 100, right? So I don't need actually, anyways, if I write just write n2 in terms of n1, n1 will automatically get cancelled out. So this will be 18 divided by 23 into n1 minus n1 divided by n1 into 100%, right? So this will be equals to minus 5 by 23 into 100%, right? Okay, so 5 divided by 23 into 100, so minus 21.74%. So speed is reducing actually because the back EMF has reduced. So minus 21.74%. So negative sign here signifies that speed reduction. Okay, this was for the case 1. Now let's do for the case 2. So the case 2, they are telling me that the torque has been halved. So in the case 2, flux won't change, right? Phi 1 is equals to phi 2, that will be constant, but T2 equals to T1 by 2. So what will happen to the armature current? So from here, from this relationship, I can directly say that armature current IA is proportional to torque divided by flux, correct? So if flux is constant, if torque is reducing by half, so the armature current also will reduce by half. So I can say over here that my IA2 will be half of IA1. So what was IA1? IA1 was 50 amperes, if I remember correctly. IA1 was 50 amperes, so it will be 50 divided by 2. So it will be 25 amperes. So from here I can directly write what is my terminal voltage, right? Or what is the developed voltage, because I have to ultimately find out the change in speed. So this time EB2 will be what? Again, terminal voltage minus IA2 into the additional resistance 1 plus 0.2, right? 0.2 plus 1, 0.2, the armature resistance plus the additional series resistance. So V is 240 minus 25 into 1.2. So 25 into 1.2, 30. So this will be 210 volts. Okay, so EB2 is 210 volts. So again I can use the speed formula. So speed does not depend on load current, it depends on the flux, it depends on the number of conductors, it depends on the flux per pole. So again same relation, right? EB1 upon EB2 will be equals to N1 upon N2. So from here I can directly write what is my N2. N2 is equals to EB1. EB1 is basically 230, right? 230 volts. Sorry, it should be, sorry, EB2 by EB1. So EB2 is 210 volts into N1. N1 is N1. I don't know N1, right? So again the percentage change. So percentage change again this time in speed will be same thing, right? Same formula. So it will be 21 divided by 23 minus 21 divided by 23 N1 minus N1. This time it will be lower as the load torque has been reduced, right? So speed reduction will be lower divided by N1 into 100. So this will be 2 divided by 23 into 100. So minus now the reduction will be minus 8.7 percentage. Okay, This will be the reduction basically. Minus 8.7 percentage. This will be the answer of this question. So in the second case, if the load torque is also halved, it will be minus 8.7%, and in the first case, it will be minus 21.74 percentage. Okay. So yeah, I hope you have understood. So I want you guys to try out these two questions. So this question and this question, and I guess yeah, these two questions I want you to try it out by yourself, and I will come back with the solutions. Let's solve this question. A DC shunt motor with an armature resistance. Just hold on a second. Yeah, I have a DC shunt motor with armature resistance as 0.2 ohms and operates at a RPM of 1245 revolutions per minute while drawing an armature current of 125 amperes. So it draws an armature current of 125 amperes from a 440 volt supply. So it terminal voltage is 440 volts, right? If the field excitation is reduced by 75%, so the field excitation is reduced to 75% of the original value. So my phi 2, if the excitation is reduced, basically what is my phi 2? Phi 2 is mmf upon reluctance, right? So reluctance will not change, it is a constant value, right? Physical, it is a geometric value, depends on geometric parameters. mmf is n into I. So again, number of turns you will not change, right? You will not go into the machine and change the number of turns. So if the excitation is reduced by 0.75, that means basically the current has been reduced by 0.75, right? So my flux phi 2 will be field excitation is reduced to 75% of its original value. So my phi 2 will be 0.75 of its original initial value. Okay, that is what my phi 2 is equals to. Okay, now we will discuss and the total torque developed by the armature remains unchanged. So my T2 is not changed. T2 is equals to T1. Determine the new speed of the motor in RPM. Very simple, right? Because we have already discussed that my torque is proportional to the flux and the armature current. So flux is getting reduced, but torque is same. So what will happen? What is my armature current proportional to? So my armature current is proportional to torque by flux, right? So it is inversely proportional to the flux because torque is constant. So armature current is inversely proportional to flux. So Ia1 by Ia2 will be equals to phi 2 by phi 1 as it is inversely proportional. So what is phi 2 by phi 1? Phi 2 by phi 1 is 0.75. So my Ia1 or Ia2 is equals to Ia1 divided by 0.75. Divided by 0.75. Okay, so yeah, what I can say here is, so they have told me the Ia1 current 125 amperes, right? So I can find out the Ia2. Why do I need to find out the Ia2? Because ultimately I want to find out the speed. For me to find out the speed, I need the back EMF, right? And to find out the back EMF, I will need the current. That's why. So Ia1 initial current, armature current is 125 amperes, right? So it is 125 divided by 0.75. Okay, so this will be if I do this 125 divided by 0.75, so this will be 166.67 amperes. Okay, now yeah, now this is my Ia2. What will be my EB2? EB2 will be simply terminal voltage minus Ia2 into RA. So V will be, what is the terminal voltage? Terminal voltage is 440 volts minus Ia2 is 166.67. 440 minus 166.67 into RA. So what is my RA? RA is 0.2 ohms. So RA is 0.2, right? So this will be into 0.2 plus 440. So this will be 406.67 volts. Okay, so this will be my back EMF in the second case. So again I can simply solve this. What is the back EMF in the first case? I have not yet solved it. So back EMF in the first case will be V minus, this will be IA1 into RA. So V is 440 volt, it will not change. IA1 is 125 amperes into RA 0.2, right? So this will be equals to 125 into 0.2 plus 440, so this will be 415 volts. So from, and the speed is 1245, so I can use the same formula, EB1 by EB2. Is it directly proportional to the speed anymore? No, because flux is also changing, right? So it will be phi1 n1 divided by phi2 n2, because your back EMF is proportional to both the flux and the field, both the flux and the rotation speed, right? And number of turns, number of conductors and number of poles will be fixed because it is a geometrical parameter. So this will be EB1 is how much? EB1 is 415 and EB2 is 406.67 equals to, now phi 1 by phi 2. So phi 1 by phi 2 is this, right? Phi 1 by phi 2 is this. So phi 1 by phi 2 is 1 by 0.75. So it will be 1 divided by 0.75 into n1 divided by n2. So n1, I know n1 is 1245 and n2 I have to find it out, right? N2 I have to find it out. So N2 will be basically this divided by 406.67 into 0.75 divided by 1245. Okay, somewhere I have messed up something. No. Yeah, this is where I messed up. So 1245 into 1245 into 406.67 divided by 0.75. Okay, sorry, into 0.72 divided by 0.75 and divide by 415. So 1626. Okay, so 1626.68 RPM will be the speed in the second case. I think that is what they have asked, right? What determine the new speed, right? We have to determine the new speed. So the new speed in RPM will be 1626 RPM. This will be the answer. Like, these are very basic questions, just whatever relation we know, we are just using those relations, right? So let's solve this next question. A shunt connected DC motor operates at its rated terminal voltage. Its no load speed is 200 radian per second, right? Okay, so now they have given me in radian per second. So they have given me small n. So small n or omega equals to 200 radians per second, right? So from here I can easily find out what is the rotation per minute. Okay, it is a no load speed. So this is the no load, right? Remember, this is the no load speed at its rated torque of 500 rpm when it is loaded. So no load means torque is 0. Here the torque is 0 because no load torque is there, right? No load means it is open. I mean, not open, sorry. I mean, I am not providing it any load. So there is no load. So torque is 0, right? Now, when it is loaded, that is a rated condition. So rated condition is the rated condition, torque rated is 500 Newton meter. At rated condition, the speed will be somewhat lower. It is telling us that the speed at full load or rated condition is 180 radian per second. Okay. The motor is used to directly drive a load whose load torque depends on rotational speed. So I have a load whose load torque is a function of the speed itself, right? At what speed it is rotating, the load torque is function of that, such that it is 2.78 into omega r. Neglecting the steady state, neglecting losses, the steady state speed of the motor when it drives this load. So one thing you have to keep in mind is that here I have a motor, right, and here I have a shaft. So let's say if no load was there, so this was simply rotating bindas, this was no problem with this, right? This was simply rotating, no load was connected. As soon as I connect load, what will happen? If you ever observe that initially when you start the motor, it is very fast, right? As soon as you connect a load or something, it slows down. The motor slows down. Why does it slow down? Because there is a balance equation. So the motor is driving this shaft at a developed torque known as T developed. And as soon as I provide a load, the load will oppose the T developed, right? Due to its inertia weight, it will oppose in the opposite direction. This will be the T load. And what is happening? So it is same like this, right? Same like a box. If I have a simple box here and I am applying some force here, right? And let's say I want to keep this in steady state, what will happen? I have to apply another force of equal magnitude in opposite direction, F, right? What will happen then? Will the box be in steady state? Will the box be in rest? No, right? Because let's say initially this force was there, then I applied a force in the opposite direction. So whatever that velocity it has, it will just keep that velocity, right? So whatever motion it was in, it will be in that motion. It will not accelerate. The box will not accelerate. Basic physics, right? The block will not accelerate. Same thing here as well. As soon as I will connect a load here, what will happen is it is just like friction, right? The developed torque is in this direction. The load torque will be in opposite direction, and at balance condition, steady state condition, that load torque and the developed torque will be same. At that point of time, the speed will be constant. Same like here, right? Here, if I apply a force of equal magnitude in opposite direction, the velocity will be constant in this case. Okay. So same principle will apply here. So how will I equate these two, right? Because the developed torque must be equals to the load torque. So for that, first of all, I will draw the speed torque characteristics of the machine, because they have given me that at no load speed is this and the full load speed is this, right? And the torque is changing like this. So at no load, the torque will be 0 because no load is connected. So there is no torque connected, right? So if I draw the graph of the machine, the torque speed characteristics of the machine, so it will be somewhat like this. So this will be the speed and this will be the torque, right? So in this case, the torque speed graph is somewhat like this, that at no load, when the torque is 0, the speed is obviously the highest value, that is what? That is 200 radian per second. So here the speed is 200, okay, not this, 200 radian per second. Okay. Now if I keep on increasing the load torque, if I keep on increasing the load torque, so not load torque, whatever torque that is there, then what will happen? The speed will reduce and it will reduce to 180 radian per second, right? It will reduce to here 180 radian per second. Okay. So and it will be a linear graph, right? Why it will be linear? Can someone tell me why it will be linear graph? That why this will reduce linearly? So one thing like I forgot to mention is that actually I should have taken this question after learning the speed torque characteristics, right? So assumption is the speed torque characteristics will be linear as nothing is mentioned. So we have to make an assumption, or you can leave this question now. We can you can watch this after the speed torque characteristics. So a mistake on my behalf. So we will assume the like speed torque to be linearly varying. So at full load, they have given me the torque value, that is 500 Newton meters, right? So from here I can write the equation of the speed torque. So from here I can see what is the slope. Slope will be minus 20 by, so omega will be equals to minus 20 by 500. So it will be minus t by 25, and initial when t is 0, it is 200 radian per second, right? So what have I told you? I have told you that this is my speed of the rotor, right? and at steady state my load torque and this is the developed torque, right, across the motor. Load torque and the developed torque will be equal. So what is the equation of the load torque for the load, right? It is TL equals to point TL equals to 2.78 into omega r into omega r, right? 2.78 into omega r. So I can replace this TL here, right, because TL will be equals to TD, so I can replace. So I get the equation omega r equals to minus 2.78 omega r divided by 25 plus 200, right? So from here I can actually get the value of omega r. So 2.78 divided by 25 plus 1 into 200, so it will be 179. So my omega r will be 180, almost approximately 180. Okay, it will be on almost full load only. It will be approximately full load only. Okay, 180 radian per second. Okay, so approximately also, like, although even though they have not given you, but you can see that my load torque is this, right? If my load torque is this, for what value of omega r it's satisfied. If I put here the rated speed here, if I put 180 here, I see that it is satisfying the rated condition. So even though actually this is not exactly correct, I don't know what is the graph, but without the graph as well, if I put here the rated value, right, if I put here omega r equals to the rated value, that is 180, I see that it is satisfying, that is it is equals to 500 newton meter. And when does it reach steady state? When the load torque and developed torque is same. So that means the 180 radian per second is the correct answer for this question. Okay, so bit of mistake is there, they should have mentioned what kind of characteristics the graph is. But if I somehow put the value of the full load torque here, I will get the omega r, right? Omega r will be satisfying these relation. So that means it is operating in full load. So I can say load is operating in full load. Okay, now let's discuss about the next one, that is series wound DC machine, right? So in case of series wound DC machine, basically the field winding, instead of it connecting in parallel to the armature, it will be in series with the armature. That's why the name series wound DC machine. So field winding is connected in series with the armature, so it carries entire armature current. So whatever the current across the armature, same current will flow through the series. Now, as I know, the armature current is generally very high, right? Because it supplies the load as well, and load current is generally very high. So my field current now also increases very high, right? So my MMF, like I cannot go very high MMF, else the core will saturate. So MMF again is going very high, correct? So I have to reduce the number of turns. So that's why the field winding will have lower number of turns. And again, if the current is higher, then the wire must be thicker, right? It has to support high amount of current. So current density is constant, so wire will be thicker, wire will be more thicker. Okay, that is a case that you must understand over here. Now let's write down few equations. So this is the intuition that I wanted to give you, how the field winding of the series machine will be, DC series machine. Now let's write down the equations again. This time things become very simple. This time my armature current is same as the field current, right? Same as the field current, IL or IS, whatever is the supply current, is the same as the armature current, is the same as the series field winding current. I'm deriving it for the generator. Okay, what will be the generated voltage now? EG. Now EG will be the, as it is a generator, so it will provide both the drop across the armature and across the field winding. So this will be EG will be equals to the drop across the, EG will be equals to the supply voltage, of course, plus the drop across the field winding, plus IF into RAC plus this IA into RA, correct? So IF is simply IAC only, so it is basically equals to VS plus IA into RAC plus RA. Okay, very simple and easy to understand. Again, we can do the same exercise, that I can multiply here IA on both sides. This will be EG into IA. This will be the power available at the shaft. This will be equals to VS into IA, that is the output power, plus IA square into the copper loss in the series winding plus the copper loss in the armature winding, right? Self explanatory, the losses, these are the losses and this is the output power. Very simple, right? So again the same thing, my input power will be equals to output power plus the losses, all the copper losses, the field winding copper loss and the copper loss, armature winding copper loss. Okay, so now let's derive it for the motor. Same thing, right? Instead of I'm delivering, instead of the like machine delivering, it will now absorb the power, right? Because the motor will rotate, so it absorbs the power. So supply will send the power now. So this time my IS, again same equation, IS is equals to IA equals to ISE, but the back EMF this time will be the subtraction of the drop across here and across here, across the armature and the field winding. So VS EB will be back EMF will be equals to VS minus IRA drop across the armature minus the IA RAC drop across the series field winding. Again the same exercise you can do, whatever is the armature power you can calculate that power. So this input power is also known as the shaft power, right? Shaft power or the armature power, anything will work. Okay, so that was about the this derivations. So whatever we have discussed, same thing is written over here. Why it is connected in series to handle high currents, it has to be of thick wire, and basically resistance will be lower to minimize the losses. What is the losses? Losses is IA square RAC, right? So I have to minimize losses, right? So how will I minimize the losses? IA square RAC. So again, area is more, area is high, the resistance will be lower. So this I have to minimize. So I will minimize this by reducing RAC, because current I cannot minimize, it is the load current, right? I cannot minimize the current. Okay, so now let's solve few basic questions on this series winding. So let's solve this first question. A 250 volt DC motor, series motor, has an armature resistance of 0.25 ohms. So my RA, always in case of DC machines, always start writing the data 0.25 ohms. Okay, and a series field resistance RAC of 0.15. First thing what you observe is the series field resistance is much smaller than the shunt field resistance that we have been seeing, and it should be like that only, right? That is what we have discussed. So yeah, this is fine. Determine the current required to produce a torque of, in the case 1, to produce a torque of 80 Newton meter at a speed of 1200 rpm. Okay, so let's solve the first one first, then we will discuss the second one. So I know this is the torque, load torque, and this is the speed, and this is a DC series motor. It is a motor, 250 volt motor. So 250 volt motor means the terminal voltage will be 250 volts. Okay, so I have to, how much power I need to, what they are asking, how much current I need to supply so that it can produce a load torque of this much and speed of this much. So again, what is the shaft power? It is omega into T, right? Or omega is 2 pi n by 60 into T. Okay, so this will be equals to the whatever supply is supplying, right? So how much power supply is supplying, basically Vs into Ia armature current plus the losses. This is the equation, right? This is the, so this is the armature, this is the EB, this is EB, right? So either I can find out the armature current directly, EB into Ia, this will be equals to EB into Ia, right? And what is EB into Ia? What is EB? EB is basically Vs, this is Vs, minus the drop across the series resistance of the field winding and the armature resistance, right? So we get back the same equation only, that it is equals to Vs into Ia minus Ia square into RSC plus RA. Okay, yeah, that is it basically. So what I can say here is that uh, so what I can say is now what do I need to find out? I know the I have to find out the armature current only, right? So I know all this value, right? Do I know EB? So EB, actually I can find out EB, right? Oh, I cannot find out EB. So this is the equation only. This is the equation only. So I think I have to solve the quadratic. I have to solve the quadratic. If I don't solve the quadratic, I will not be able to solve it. Okay. So I know what is omega, like what is n into t. N is given, t is given, right? So it is basically 2 pi divided by 60 into n, that is 1200 rpm into at equals to Vs is 250 volts into Ia, which I have to find out, minus. So in case of series field winding, right, we sometimes have to solve the quadratic equation. Most cases you will see this case, it will be Ia square into RAC plus RA. RAC is how much? 0.15, RA is 0.25, so this will be 0.4, right? So if I take this Ia square on the left hand side and if I divide by 0.4, this will be, if I want to calculate, this will be 2 pi 2 into pi divided by 60 into 1200 divided by 0.4, 340, right? This is 80, yeah, this will be 314 something, 314. So 300 and okay, 314.16, and what is this? 250 divided by 0.4, so minus 625 Ia. Okay, equals to 0. So from here I can solve the quadratic equation, and from here I can find the Ia. So this Ia will be 625 minus plus minus of b minus b square minus 4ac. So 4 into 314, this is my Ia. So 625 whole square minus 4 into 314.16 whole under root. Okay, I is coming pretty small. Any mistakes? I think I'm making a mistake. Just hold on. 2 into pi into 1200 into 80 divided by 60 divided by 0.4. Yeah, I made a mistake. This should have been 25132 actually. Okay, my bad. 25132.74. So this should be 25. That is what I was thinking, that how can it be this less, plus 625 whole square. Yeah, now it seems, yeah, this is 538. So 538, I cannot choose, there can be two values. So this, right, now Ia can have two values, plus minus 538, correct? Which one shall I choose? You will decide, right? You will tell me which one shall I choose. So this will be equals to, either I can choose the negative and the positive. Which one shall I choose and which one shall I reject? Okay, so plus 625 is 86.4 divided by 2, so it becomes 43.2. One of the answer is 43.2. What is the other one? 625 plus 538 divided by 2. So this will be 581.5 ampere. Okay, now which one will you choose? Will you choose this one or this one? So if we choose this one, right, what will happen? Your EB will come out to be negative. Is it possible? No, back EMF in this case is not possible. Back EMF in case of braking only it can come negative, otherwise it will not. So if I choose the second one, right, if I choose the second one, that is like it, first of all it is very high current, anyways we will not choose it. But if you still want to choose the second current, what will be the back EMF developed due to the second current? So it will be Vs minus Ia into Ra plus Rac. So Vs is how much? Vs is, it is 250, right? 250 minus it is 581.5 into Ra plus Rac. Ra is this is 0.4, right? This will be 0.4. So this into 0.4, if I subtract, so I see very less amount of back EMF is getting developed, like only 17.4 volts, right? Very low amount of back EMF is getting developed. This is not the case. This is not the correct case. Some like this is huge. First of all, this is huge current, right? Very high current. Very low back EMF is getting developed. So this we will neglect. This solution we will neglect. We will take this solution. This is the correct one. Okay, this solution will be the correct one. Okay, we will always neglect the, most cases we will always neglect the high current, right? Because the winding may burn, right? Very high current. So these kind of this case will be chosen where this is the case for which at starting when the machine will start, then it takes very high current, because then the back EMF is very low. As the machine has reached steady state, the back EMF will be high, right? Because it is rotating with a speed. Okay, so that is the case over here. So because this is the case when machine is starting, so this back EMF is this much low when the machine is starting, but here they have already told me that the machine is rotating at a speed of 1200 rpm, very high speed, right? So I will neglect this case. I will neglect that case. So the armature current will be 43.2 ampere. This will be the answer for the first part. Okay, now let's solve for the second part. For the second part, what will be the answer? Okay, for the second part, how will I solve it? If the motor runs at 1800 rpm with half of this current, calculate the percentage reduction in flux. So now if the motor is running at 1800 rpm with half of this current, calculate the percentage reduction in the flux. How much flux has been reduced, right? So now what will the flux be? What will the flux depend on this time? So my flux, right? I know my induced voltage EB is proportional to the flux and the speed, right? Because number of conductors is fixed generally and the poles is fixed. So ultimately it is dependent on this. So I can write here my flux, right, is dependent on EB upon speed. Now what they are telling me that the current IA2 has been halved, right? That is what they are telling me. If the current has been halved, right, half of this current, and the speed has been increased to 1800 rpm. So speed now, previously it was 15 or 1200 rpm, right? Speed was 1200 rpm. Now the speed has been increased to 1800 rpm. So N2 by N1 is 1800 by 1200. Speed has been increased to 1800. So what will be the change in flux? That is what we have to calculate. So I can write here current has been reduced. So from this, right, from this information I can directly calculate the change in the back EMF. So what is EB1? EB1 which we have already, okay, which we have not already computed, I will compute. It will be Vs minus Ia1 into Ra plus Rac, right? Ra into Rac. Okay, so what is my Vs? Vs is 250 volts. minus IA1. IA1 is basically IA1 is basically 43.2 into RA plus RAC. RA is like RA plus RAC is 0.4, right? So this value will be 250 43.2 into 0.4 plus 250. This value will be 232.72 volts. This will be my back EMF here. Okay. Now, in the first case, in the second case, current has been reduced, right? So current has been halved. So it will be again Vs minus IA2 into RA plus RAC. So it has been halved now. So it will be 43.2 divided by 2 into 0.4. This will be 54. Okay, so not divided by 0.4 into 0.4. So 8.6, right? 8.6 plus 250. Sorry. Minus 25 plus 250. Yes, 241.36. This will be the voltage in the second case. Now I can simply take the ratios, right? I can simply take the ratios that my flux phi 1, because I have to calculate the percentage change. So I just have to find out the ratio, right? Phi 2 by phi 1 will be what? It will be EB2 by N2 divided by EB1 divided by N1. Okay. So so it is basically EB2 by EB1 into N1 by N2, right? So EB2 by EB1, EB2, so phi 2 by phi 1 will be 241.36 divided by 232.36 into N1 by N2. So N1 speed is, initial speed is 1200 and final speed is 1800, right? From here I can directly find out the ratio. So this divided by 232.36 into 1200 divided by 1800. This is equals to 0.6925. Okay, so I can simply find out the percentage change. So percentage change in flux will be what? It will be phi 2 minus phi 1 divided by phi 1 into 100%. Okay, so this will be what? This will be 0. Okay, for phi 2 is 0.6, so flux will reduce basically. So it will be 0.6925 minus sorry, this will be phi 1 minus phi 1 divided by phi 1 into 100%. So this value will be minus 1. So it's like negative 30%, negative. So flux will reduce, negative sign denotes that there is reduction 30.75%. Okay, this much amount of flux reduction there will be. So this will be the answer basically. Percentage change will be reduction by 30.75%. Okay, this is the answer for the second part, right? Yeah, second part answer. So this is how you mainly solve the questions. So that was about this question. Now let's start with the next type of DC machine, which is known as the compound DC machines. So in compound there are many types of DC machines. One is known as short shunt and long shunt. Compound means it is mixture of both, right? That is what compound means. Compound is a mixture of both. We want to take advantage of both shunt and series. So the field windings will be present both in series with the armature and in parallel with the armature. Now there are two ways in which I can place my shunt and series field windings. One is the short shunt. So in case of short shunt, so the shunt field winding will be connected directly across the armature and the series field winding will be connected outside here, right? And what is a long shunt? So long shunt is the shunt where the series field winding will be directly connected in series with the armature and the shunt will be connected here, not directly across the armature, not directly in parallel with the armature, but in parallel with the combination of the series winding and the armature. Okay, that is the difference between your long shunt. Long shunt means basically more wire is required here, that's why it is called long shunt, and the short shunt conformation. So again, KVL KCL, right? Very simple KVL KCL. In case of short shunt, the series current IAC current will be, let me use white color. IEC current will be equals to IS, okay, or the supply current in case of generator, right? And the shunt, right, shunt current or the shunt field current will be what? So the shunt field current will be whatever the voltage that is coming across here, that is after this drop, right? So ISH will be Vs minus the drop across the series field winding, so it will be minus ISC into RAC divided by your shunt resistance. So this will be the shunt current and the shunt series current, right? Series field winding current and the shunt field winding current, pretty easy and self-explanatory. So okay, one more thing. Okay, sorry. This, right, we are discussing about the generator. So for a generator, EG is supplying both to the load and to the shunt, right? So one mistake I have made. So current directions will be what? Current direction will be IA will be equals to ISH plus IS. So just a small mistake. Okay, ISH plus ISC. One slight mistake, because this is for the motor actually, this ISH, but for a generator what will happen? For a generator I will write in terms of EG will be the developed voltage, right? So it will be EG because this extra drop will be there, right? So overall voltage will be this EG plus this drop IRA, EG plus, sorry, no, sorry, not this drop, EG minus IRA, right? EG minus IRA, because this will develop the voltage like this, current will leave from the positive terminal and the drop across the RA will be like this, so it is opposite, right? So it is EG minus IRA divided by the shunt resistance RSH. So this is how you will find out the shunt current, right? Or otherwise also you can write this in other way. How you can write this? You can write this. Okay, this also, no, this will be what? So what is the drop here? So for a generator, the drop will be like this, right? Plus minus, correct? And this is also plus minus Vs. So it will be Vs plus the drop across the series resistance. So I SE or IS into RSE divided by the shunt resistance. Both are saying the same thing only. Okay, yeah, so that is the thing over here. So now what I can do is I can okay, for a motor, this is for a generator, right? This was for a generator. For a motor, just the opposite. This time Vs will supply, so Is will be, this time my Is will be equals to IA plus ISH, and again the same thing, that my series winding current is same as the supply current IS, right? And ISH will be this value now, because this time the drop is like this, plus minus, right? This is plus minus, this is plus minus, so it is opposite sign, drop is opposite, so this will be Vs minus ISC into RSC divided by RSH, or you can write this in terms of back EMF as well, KVL, KCL. I know you guys are expert in long shunt. So in long shunt, just bit of things will be different here. So now my series current will not be equal to the supply current, it will be equal to the armature current. That is the difference for a long shunt, right? Everything else is almost same, that my armature current in case of a generator will be equals to the sum of the supply current plus the shunt current. And how do I find out the shunt current this time? So shunt current is directly connected across the supply now, so my shunt current will be ISH will be Vs divided by RSH, right? Or you can write it in terms of the generated voltage Eg plus the drop across this, plus minus, so there will be some drop across this, there will be some drop across this, so not plus, sorry, minus IA into RA, drop across the armature, minus drop across the series winding IAC into RAC. Okay, this value will be divided by RSH, and from here you can simply find out the shunt current. Okay, more than enough, this is more than enough. And same thing you can derive for a motor. I'm leaving it up to you guys, you guys are very good, so you guys will be able to do it. So this was about the long shunt and the short shunt. Okay, now one more thing is there, how can I control the direction of the magnetic flux, right? So let's say if I have two windings here, if I want to control, so if you remember, are these two pictures same? No, right? They are not same. So the orientation is different here. Orientation is different. And if you remember, in case of dot, right, whenever we are learning about transformers, so their dot convention we used to use. So their orientation, if I used to change the orientation, the place at which the dot will come used to change. Same thing will happen here. So in the first case, the current is like this, right? It will be like this. So if I use my right hand basically fingers, so if I curl my fingers along the direction of the current, I am seeing that the magnetic field is in the upward direction now. What if I wanted to change this magnetic field directions? How will I change this magnetic field directions? So what will I do is, now in the second case, what is the direction of the current? Although it is incoming only, but I have changed the orientation. So current is something like this, right? Current is something like this. This is the field current, right? So this time if I curl my fingers along the current direction, it is downwards. So it will be downwards. It will be downwards. So flux will be downwards. Okay, so that's how we can change the direction of the flux by changing the orientation. So this is what we will do actually. So we will, the shunt field winding and the series field winding, we will change the orientation so that in one case both of them are supporting, both the field flux are supporting each other, in the other case both of them are differential. So from this we can further derive our compound DC machines, that one will be cumulative. Cumulative means both the flux are aiding each other. So flux total will be flux in the shunt plus flux in the series, right? So it all depends on the orientation, how am I orienting the windings on the pole, right? It all depends on that. So cumulative compound machine is a machine in which both the series field flux and the shunt field flux will both aid each other. So here it is in this configuration, the flux produced by the series and the shunt field will aid each other. So we show diagrammatically like this, that both the fluxes are in the same direction. Both the fluxes are in the same direction. Same diagram you can draw for a motor, no problem. Same diagram you can draw for a motor. Now, what is the other type of compound machine? Differential compound machine. In differential compound machine, one flux will oppose the other. Now, we don't know which one is dominating. I don't know. Whichever one will have higher magnitude. So the flux, overall flux will be in that direction. Okay. So here the flux produced by the series field winding opposes the shunt field winding and vice versa. Right. So effect this opposition weakens the overall flux. Here the overall flux is increased. So can you tell me what will happen to the speed or the back EMF? So my back EMF or generated EMF, anything you want to write, is proportional to the flux and the speed, right? So if in case of generator, if I rotate it in the same speed and if the flux is increased, then the generated EMF will be increased. It is a good thing, right? I can support more load. And if it's a motor, if I am providing it some constant back EMF or constant current, if the flux is reduced, the speed will increase further. If the flux is increased, then the speed will reduce further. If the flux here is increased, speed will reduce. That is what will happen in the cumulative if the back EMF is assumed to be constant. In differential, overall the flux is reducing, so the generated voltage also will reduce. Okay, generated voltage also will reduce. How do I show it diagrammatically? That both are in opposite direction like this. So one is in the right hand side, other one is in the left hand side. So that means they are opposing each other. Okay. So again, if flux reduces, overall generated EMF also will reduce. Okay. If speed is assumed to be constant, if I am talking about generated EMF, right? Now, if the what do I say? If the overall, if the for a motor, if the back EMF is fixed, right, and if the flux is reducing, then the speed will increase. Just the opposite in case of cumulative, right? So it is not generally used because it has poor voltage regulation, because the voltage will reduce, right? Voltage will reduce, right? It's for a generator, voltage will reduce. Can be used in special purpose where decreasing voltage with load is desired. Okay, because if I connect more and more load, this series field winding will be more and more higher. So what will happen? The flux, overall flux will reduce because this phi series will increase because load is increasing, and then phi series is increasing. So overall total flux will reduce. So of course the generated EMF also will reduce. So generally used in special purposes, right? Like arc welding, and it is generally used in elevators, hoist, conveyors, where I need better voltage regulation, because with increase in load, what is happening? The generated EMF is also increasing. Okay, that's why it is used in places where I need good voltage regulation. So voltage regulation, you guys already know what is voltage regulation. A compound generator operating in cumulative mode is generating an EMF of 220 volts. So it is cumulative mode, it is a compound generator. So it is, so my overall flux, right, will be sum of the shunt flux plus the series flux. Okay. If the series field winding is suddenly short circuited. So if the series field winding is suddenly short circuited, so I have a field winding here and it is suddenly short circuited. If it is suddenly short circuited, basically whole of it is bypass, right? So my machine is here it is operating commutative mode. They have not mentioned long or short, I don't care, but I have this, like this armature is there, right? Machine is there, correct? And they have told me that the series field winding is short circuited. That means none of the current will flow through the actual winding, all of it will flow through the short circuit path, right? It is a generator, so generator direction will be something like this, right? Okay. So no current is flowing through the field winding, so no MMF is produced. So here the flux series will suddenly become zero. So overall flux total, it will just behave as a shunt. It will just behave as a shunt generator. That's it. Just behave as a shunt generator. What will be the resulting induced EMF? Okay. What will be the resulting induced EMF? That is what they're asking. So actually here, right, I cannot directly say because information is not given, speed and all those things are not given, but something I can say surely, that question is not complete actually. What I can say surely, that my E, right, my E is proportional to flux and speed, right, and as it is a generator, so speed will be constant. as it is a generator, correct? Because I rotate the prime mover at some constant speed. So I see that the overall flux previously what phi AC plus phi SH, now the flux has become change phi T has changed to phi SH only. So of course the overall flux has reduced. So if overall flux has reduced, so the generated EMF also will reduce simply. EG also will reduce. That's it, right? So basically my current EMF will be somewhat lower than the previous EMF 220 volts because generated EMF will reduce. Okay, that is the solution basically. Okay, yeah, that's it basically. Now same thing if I'm doing now, if the compound generator is operating in differential mode and again if I short circuit the series field winding, now what will happen? Again my overall flux, right, this time is, it is not cumulative, it is differential. So it is phi SH minus phi AC. So if I suddenly short circuit, so my phi AC will become 0 because my IAC current will be 0. So all of the current will flow through the short circuit. So my, what is happening? Overall flux now is phi SH. Previously it was phi SH minus phi AC. So my flux total has increased. So what will happen? Basically my generated EMF also will be increased because EG is proportional to flux into speed, but speed I have assumed, as it is a generator, speed I have assumed it to be constant. So if I assume speed to be constant, so my flux is increasing, so my EG generated EMF also will increase. So this time the EMF, right, value induced EMF will be somewhat more than 220 volts. Okay, so this is the intuitive idea that we can understand from a differential and cumulative compound mode. Okay, so let me delete this page. Yeah, let me solve another question. So this is the 10th question. So a cumulative compound motor produces a torque of 200 Newton meter at a speed of 1500 rpm. What will be the effect on torque and speed if the series field is short circuited or the shunt field is opened? Okay, so both cases same thing will happen, right? So it is operating in cumulative mode. So if it is operating in cumulative mode, if the series field is short circuited, then my phi AC will be 0, or if the shunt field is open, so current across the shunt field will be 0, so again my phi ACH will be 0. So either you are making series field to be 0 or shunt field to be 0. If you are making series field to be 0 or shunt field to be 0, it basically means what? It basically means overall flux, right? Phi total is what? Phi total is phi AC plus phi SH cumulative mode. So overall flux is reducing, flux total is reducing, so phi T is actually reducing. Okay, so if phi T is actually reducing, that means what? That means my generated EMF will reduce. Okay, but I am using it as a motor, I am using it as a motor. So assumption is that my what is my flux proportional to? Flux is proportional to, in case of motor, it is proportional to the back EMF by the speed. Correct? Back EMF by the speed. So if flux reduces, and if I assume that the back EMF is assumed to be constant, then the speed has to increase. If flux is reducing, and if I assume, okay, what is my back EMF equals to, if you remember, yeah, this only back EMF. So one more thing, they are discussing about torque, so I will discuss about torque as well. So torque, what is torque equals to? Torque is equals to torque is proportional to phi into I, right? That we had derived in today's lecture only, phi into I, correct? So like we are just comparing with respect to speed here or the flux. So assumption is, as the supply voltage Vs is not changing, hence the EB voltage will also change very little. Okay, no change, constant. So I can write that my flux is inversely proportional to speed if I assume my back EMF to be constant. So okay, so my speed will, like flux is reducing, right? If flux is reducing, then speed will increase. It follows inverse relationship. So speed increases. What about torque? So if flux reduces, so torque also will reduce. Assumption is if the load current is fixed. If the load current is fixed, if flux reduces, torque also will reduce. Because they have not discussed about other components, I will assume those to be constant. So if speed increase and torque will decrease, so option A will be the correct answer in this case. Okay, nothing is mentioned about the other components, so I will assume those to be constant. Okay, so these are the key comparison basically, that for a cumulative mode flux will aid each other, for differential flux will oppose each other. Total flux increases under load. So if load is there, current will flow through the series winding, so the flux will increase. It decreases because if current flows through the series winding, so phi total is phi sh minus phi series. So of course, if phi series is increasing, so total flux will reduce. Voltage regulation will be better here mentioned, as because due to the generator overall flux increases. Here it will be poor because with loading the voltage drops because the overall flux drops. Okay, this is widely used, this is rarely used. So these are the few examples of a compound motor. So let's solve a question whatever we have learned till now and try to apply that. So we have a 250 volt compound generator that has armature, series field, shunt field resistance given. So we'll keep on writing. So the armature resistance Ra is 0.4 ohms and the shunt field resistance RSH is 0.2 ohms and the series field resistance RAC is 125 ohms. Okay, so these are the information. The shunt field resistance is this and the series field resistance is 0.2 ohms. Okay, the generator delivers 10 kilowatt at rated voltage. So it delivers 10 kilowatt, that means in the supply load it is delivering 10 kilowatt. Okay, very important to understand, it is delivering 10 kilowatt, that means my like power delivered P load is 10 kilowatt. Okay, at rated voltage. So rated voltage of the generator is 250. So this is the terminal voltage, this is not the generated voltage, this is the terminal voltage. Keep this in mind, whenever they give the voltage they give the terminal voltage. So 250 volt is the rated voltage. Okay, so it is supplying power at rated voltage. So what will be the current? So let me just because here right they have not mentioned it operates in long shunt or short shunts. Now they are asking determine the armature EMF when the machine operates in long shunt and in short shunt. So I will have to copy both the circuits, the long shunt and the short shunt one. Okay, so roughly I will draw, I will not directly copy the actual, I mean good figure, fair figure, because I want you to know how to draw it roughly. So short shunt means what? The shunt, the wire is short, that means it will be directly connected across the armature. So it will be somewhat like this. I will have a series field RAC, right? This will be the load, that is 250 volts, and I will have this armature with its armature resistance, and I will have the generated EMF, right, EG, and it is a short shunt, so the shunt winding will be directly connected across the armature. So now I can directly say that I am delivering here power 10 kilowatt of power at 250 volts. So do I know the current here? Yes, it will be 10 kilowatt divided by 250. So it is 40 amperes. This current will be 40 amperes, correct? So this current I got to know is 40 amperes. Now basically what is my supply or load current, right? IL will be power upon the voltage, 10 kilowatt upon the voltage, that is 250. So this will be 40 amperes. Okay, now so what is the drop here? So this is 40 amperes. So what is the voltage here? The voltage here will be what? This voltage, right? Let me name it as Vx or VSH, right? VSH will be basically what? Because this is supplying the power, right? So it will be this drop plus the 250 volts. So 250 plus 40 into RAC. What is RAC? RAC is 0.2 ohms. So it is 0.2 ohms. So it is 258 volts. VSH will be 258 volts. Okay, so this is my shunt voltage. Now what I can comment, I can comment VSH is this. What is the current? ISH. Very simple, right? ISH will be what? ISH will be VSH divided by RSH. So it will be 258 divided by the shunt resistance. Shunt resistance is given as 125, right? 125. So this will be 28 divided by 125. So 2.064, right? 2.064 current will be coming here. So now what is the armature current? Because I will need the armature current to find out the EG. So armature current IA will be the sum of the shunt field current and the load current. So shunt field current is 2.064 plus the load current is 40 amperes. So the overall current will be 42.064 amperes. Okay. So this is the armature current. Now I can directly write what is EG. EG will be the sum of this drop plus this one, right? 250. So EG will be equals to IARA, drop across the armature, plus this VSH voltage, right? So I can apply KVL here, simple KVL. So VSH. So VSH is 258. Okay, 258. So now from here I will be able to write down the value of the generated voltage. So it will be IA is 42.064 into the resistance, it is 0.4. So plus 40 into 0.4, this is 16 plus 258, so it is 274.82. so 274.82 volts. Okay. So this will be the value basically. Am I correct here? Yeah, it is 258. So yeah, 258.28. Yes, this will be okay. The current will be this. So let me just do one thing. 10,000 divided by 250. Yeah, 42 into 0.4, 16 something. Yeah, so yeah, this is correct. So this is the generated voltage in the case one where it is short shunt. If it is long shunt, sorry, if it is long shunt, okay, sorry, its first case was for the long shunt. Okay, first case was for the long shunt. Okay, sorry, I solved for the short shunt. Okay, sorry. So this is for the short shunt, right? Not for the long one. My bad. So this will be the basically the second case or the part B, right? Yeah, part B. Let's solve for the part E, right? Sorry for it. So for the part E, I just forgot. So long shunt means the wire is longer, right? So here what will happen? This is my RA and this is my generated voltage, correct? And this, the series field will now be here only in series with the armature directly, and this will be the terminal voltage, that is 250 volts, and the current here will be 40 amperes, correct? So this same terminal voltage will come across the shunt as well. So what is the shunt resistance? It is 125, right? So shunt resistance is 125 ohm. So what will be the current flowing out here? The current flowing out will be 250 by 125, that is 2 amperes. So current through here will be 42 amperes. So I can directly write the EG. EG will be the drop across this plus this overall voltage. So EG will be equals to 250 plus simple KVL KCL, right? Plus IA into RA. RA is 0.4 plus RAC, that is 0.2. So this value will comes out to be into 0.6 plus 250, 275.2. So this value will come out to be 275.2. So this will be the generated EMF in the short shunt case, and in the long shunt case the generated EMF, the calculation is a bit difficult, it is 274. Okay. Now let's see the third case. If a divider with resistance of 0.3 ohms is connected in parallel with series field winding, calculate the percentage change in series field ampere turns. So this is a bit interesting. They are just asking if I have connected a diverter resistance of 0.3 with in parallel with a series field winding. So if I have a series field winding right here, I have a series field winding here, and I am connecting a resistance in parallel with this. Okay, and what is a series field winding resistance? Series field winding resistance is 0.3 ohms. So series field winding resistance is 0.3 ohms, and I already know, sorry, the diverter resistance is 0.3, series field winding resistance is 0.2. Series field winding resistance is 0.2, diverter resistance is 0.3 ohms. Okay, so uh, so uh, so what I can do is basically previously only the shunt series field winding was there. So some load current was coming here, right? IL current. It is same as the series field winding current, right? ISC. But now as there is a diverter, what will happen? If I have IL current, whole of the current will not flow through the series field winding, right? Now my ISC is not equals to IL. So previously my ISC was equals to IL. So this was my, let's say this was the flux phi 1, okay, or flux phi AC. Now the load current is same, but my IEC dash is not equals to IL anymore. Okay, previously it was equals to. So my flux, right, because the MMF has changed, ampere turns, because they have to ask me what is the percentage change in ampere turns. Percentage change in the ampere turns. Ampere turns is what? Ampere turns is basically the, what is MMF? AT. AT is basically the turns into the current across the field winding. That's it, right? So obviously the physically the terms will not change, only the current will change. Now my IAC dash is not equals to IL anymore. What is my IAC dash? So I can use the current divider rule here. So I can write my IAC dash will be equals to opposite resistance divided by the sum of the two resistance into the overall current IL. So it is now a fraction of IL. It is not equals to IL. So the current has reduced. So what is the percentage change in the MMF? So this is the part C. I am solving the part C. So the percentage, these kind of questions also can come, right? So percentage change in MMF. Percentage change in MMF will be equals to the final MMF, that is current has changed, right? 3 by 5 IL. Previously what was the series current? IL. So now it is 3 by 5 IL. Previously the current was IL, and I will compare with respect to IL only. So it will be equals to minus into 100 percentage change they have asked into 100 percentage. So this will be minus 2 by 5 into 100 percentage. This will be minus 40 percentage. So the overall MMF, new MMF will reduce by 40 percentage. So negative sign means reduction. Okay. So overall the MMF will reduce by 40%. So these are few questions about the compound generator. More questions can come. Okay. Of course, we'll discuss slowly more questions in the upcoming lectures. So we will start with the, so this was the initial two lectures which we discussed about the how to solve the DC machines, right? How to solve the circuits. So around 30 to 40% things are already covered. 30% things are already covered, right? So remaining rest of the portions we will learn after completing the construction of DC machines. So from the next lecture onwards, we will start with the construction of DC machines.